Hello, my name is Tim Morgan. My metric number is DE200111, and today I'm going to uh, present about exercise 1 simulation pulse system response for pulse system stability analysis. So, for the introduction, pulse system stability refers to the system's capacity to return to a normal state of balance following a disruption, assuming a specific beginning operation condition. So, loads, generators, outputs, generator outputs, topology, and other important operation characteristics vary continuously in the power system, which is highly nonlinear system that function in a changing environment. So when a transition disturbance, for example, occurs, the system's stability is influenced by both the origin operating conditions and the kind of disturbance. So the system must be capable of performing effectively in these circumstances and meeting the load demand. So for the scope of the activity, the scope of the present study is on the MATLAB. We are going to use MATLAB Simulink for two-area network device model power system. And then the system will be examined if there are no disturbance, and it will also focus on dynamic response resulted on by the stability of the rotor angle. Then followed by the system offers two-area networks. So system contains open two-area networks, each of which consists of a two-pair units with a rating of 900 MVA and 20 kV each. So there are several types of disturbance will be focused. For example, sudden large increment and sudden large decrement of bus 7, sudden large increment and sudden large decrement of bus 9, bus 9, and sorry, sir, temporary voltage three-phase fault at bus 5, bus 8, and bus 11, and then the permanent voltage three-phase fault at bus 8. And then for the objective to create a power system test system model using a MATLAB simulating analysis of the system dynamic reaction to the disturbances to determine if the circumstances are abrupt increases in input power and three-phase value on the transmission line may contribute to system instability. The last one is to evaluate the stability of the rotor angle of a given system under a certain sort of disturbance. Then for the methodology, so there are three methodology in this activity, which is a steady state stability, dynamic stability, and also transient stability. So that's all from me. Thank you.
Very good morning. My name is Sujisen. I'm from 2666. Now, let me continue the result for our exercise 1. Well, first one is certain large increment of log at past 7. So, the interaction in the system manifests itself at the beginning, and a certain significant increment occur at part 7 case the breaker to automatically switch to the 50% addition log that we add. As a result, the solution output apps in the examination a a well large of the stable and unstable scenario, including steady, majorly steady, and slightly unstable case for 0 to 30 seconds, and the solution was also run for 0 to 30 seconds. So this how we change how we change the volume or AT power to increase the AT power. So after that, this is the result for the certain large increment of log A part 7. Next case is certain large increment of the log at part 7. At part 7, the system it disrupt at the start, and a certain bit decrease occur as part 7. You see the breaker to immediately switch to the 50% of lower log. However, the system cannot run completely for 30 seconds because there is insufficient construction. So as a result, we also take the range of stable and unstable scenario in 1 by 8 seconds because it cannot run until 30 seconds. So, so we change the volume, decrease the volume of the log at the bus 7. So this is the result for the bus 7. After that, after that, we do the certain large increment of log at bus 9 case. So so we also we add 50% log, and then the system cannot run about 30 seconds because lack of the supply because it's too big it cannot supply that much amount. So as a result, in 1.8 seconds, we can check about the range, which part is a stable and unstable scenario. So a part scenario, we increase the volume, and then this is the result of a graph. So that we do the certain last decrement of the log at plus 9, we 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 decrease the log about 50%. So we set the range of stable, and unstable scenario for 0 to 20 seconds. So from there we analysis the stable and unstable condition. So we increase the volume at the plus 9, and then this is the graph. Next case is the temporary ordered three-phase up and bus step. So the disruptor in the system manifests itself at the beginning, and a temporary ordered phase fault occur at the bus step due to we adjust the switching time of the breaker. As a result, we analysis the unstable and stable scenario at the range of 20, the range from 0 to 20 seconds. So this we change the switching time breaker at the bus at so this is the result. After that, permanent. So permanent we adjust it the time breaker, also adjust it permanent board the three phase occurred. But the system cannot run until 20 seconds because of existing short circuit. As a result, we just take an analysis. Yeah, we just take analysis about the stable and unstable condition at the range of in the range of the 2.5 seconds. We also check the switching time, and then this graph. So next is tably broader three phase for a bus 5. So bus 5. So also say we change the switching time picking on the as a result also analysis the stable and unstable condition from the 20 and 0 to 30 seconds. So we changing for the switching time at the bus 5. So this is the result of the graph. This is the result of the graph. So last but not least, we do the last case. Well, temporarily loaded three-phase fault at bus 11. So we also do the same thing. Adjust the switching time of the breaker, but the system cannot run until 30 seconds because of an existing short circuit. So we do the analysis about about the stable and unstable condition in 2.5 seconds. So here we change the switching time at the bus level, and then this is the result of the graph. Here, it's all for me. Thank you.
Hello and a very good evening, Lecturer, to our lecturers and our fellow classmates and also Dr. Dor. My name is Richard Fine from Matrix number 819091 from Section 6, Group 6. In this part of the video, I shall be presenting on the discussions and analysis part for the results that we have acquired from the simulations that we were able to do while exercise 1. So for the first one, which is the sudden large load increment for bus 7, as shown in the red markings here, system is in an unstable state from about 0.0 seconds to 4 seconds when a sudden load increase at bus 7 happened at 1 second. Before the spike at 1 second, we could observe that the system is attempting to stabilize, but when the load increment happened, the system got unstable again. For the marginally stable case, as shown in the yellow markings, we can see that the system is heading towards equilibrium and attempted to reach stability starting at about 4 seconds all the way to 12 seconds. And for the stable case, as shown in green here, the waveforms of all the variables have straightened out at about 12 seconds to 20 seconds. Next one, for the case of sudden large load decrement at bus 7, the unstable case, as shown in the red marking here, the system is is an unstable state from about 1 second to 1.8 second when the sudden load decrease at +7 happened at about 1 second. Before the spike at 1 second, we can observe that the system is attempting to stabilize, but when the load decrement happened, the system got unstable again. And as for the marginally stable case, as shown in yellow, the system is attempting to reach equilibrium, attempted to reach stability from 0 second to 0.6 second. And for a stable case, as shown in green markings in the middle, the waveforms are all straightened out, mostly straightened out at about 0.6 second to 1 second. Okay, for next is the case of sudden large load increment for bus 9. So for the unstable case, we've got red in red here, about 1 second to 1.8 second. You can see the system is in an unstable state. As this happens because of the sudden load increase at bus 9 that happened in about 1 second. Before the spike at 1 second, we can observe that the system is attempting to stabilize, but the load increment happened, and we were able to observe that the system got out of stability from the sudden large increment. For the marginally stable case, as shown with yellow markings on the left side of the figure, we can observe that all the variables, including the rotor angles, are heading towards equilibrium and attempted to reach stability at 0 second to 0.6 second. And for the stable case, as shown in green, the system has achieved somewhat of a weak stability, as we can see some of the waveforms have straightened out about 0.6 to 1 second around here. So for the case of sudden large load decrement for bus 9, as shown in the red marking on the left, we can observe that the system, through these variables, is in an unstable state from setting at about 0 second to 3 seconds when a sudden load decrease of bus 9 happened at about 1 second. For the marginally stable case, as shown in the yellow markings in the middle of the figure above, over here, we can observe that all of the variables, including rotor angles, are heading towards equilibrium state of operation, attempted to reach stability, setting at about 3 to 12 seconds. For a stable case on the right side, we can observe that the system has achieved stability. As you can see, the waveforms for all the variables here have mostly straightened out about 12 to 20 seconds. So next one, we have temporary bolted three-phase fault at bus 8. So for the unstable case, as shown in the red marking here, we can observe that the system is in an unstable state from about 1 second to 3, when a temporary voltage 3-phase fault at bus 8 occurred at about 1 second. For the marginally stable case, as shown in yellow here, the system is heading towards equilibrium and attempted to reach stability at 3 seconds towards 10 seconds. And for the stable case, as shown in the green markings here, the system has reached equilibrium state once again from 10 to about 20 seconds. And we can see that before 1 second, the system is in a stabilized state as well. So for permanently bolted 3-phase fault at bus 8, unstable case happened over here, as shown in red on the right side of the figure, but 1.1 second to 2.5 second, we can see its system is out of equilibrium and it's unstable. And well, on one of the rotor angles remain constant, whilst the other two continue increasing angles. For marginally stable case, as shown in the yellow markings here, before the 3-phase fault occurred at 1.1 second. So this is the system attempting to stabilize itself. And for stable case, as shown in green marking here, we can observe all the variables in a stable state from about 0 to 0.25 second, while the other variables such as rotor speed, voltage magnitude, and electrical machine power are unstable from the beginning. For temporary bolted 3-phase fault at bus 5, the unstable case is shown here in the red markings. Again, about 1 to 3 seconds, the system got out of balance, got out of equilibrium, and got unstable. And this happened after 1 second here, where the fault happened. And marginally stable case from about 3 seconds to 11 seconds, the system attempted to correct itself and also trying to reach equilibrium. And for the stable case, as stated green here, 11 seconds to 20 seconds, the system reached equilibrium again and got stable. And actually before here, the system is actually stable before the fault occurred at about 1 second. And lastly, for temporary bolted 3-phase fault for bus 11, the unstable case for the system is during about 1 second to 1.25 seconds when the 3-phase fault happened, about 1 second at bus 11. And for the marginally stable case, it's 1.25 seconds and onwards, as we can see that the system is attempting to correct and adjust accordingly to reach the equilibrium state of operation, but there are still some waveforms that are out of equilibrium. And for the stable case, as shown in the green markings on the left side, we can observe that the system is already in a state of equilibrium since the beginning from the waveforms of the variables before the fault occurred at about 1 second. Alright, so I believe that's all from me. Thank you very much for having me.
As conclusion, types of disturbance influence the result and stability of the electrical system. The stability of electrical system can be defined as the ability of a system to return back to its steady state when disturbance occur. As known, power is generated by synchronous generator that operate in synchronism with the rest of the system. The fault simulated at the respective bus led to the instability for some period, with the time range may difference depends on the type of the disturbance. As we can see in the simulation, initially the disturbance occurred at bus 5 showed unstable state for 3 seconds, while the unstable state occurs at bus 8 start from 1.1 second to 2.5 second. From here, we can see the difference of the result and instability is depends on the type of disturbance occur. As all types of disturbance have simulated successfully by using MATLAB, hence the objective from this exercise have been achieved. Although there are some problems occurred when simulating the system, but we managed to overcome it as a team. All the members have give their best to complete the report. From the report writing, task distribution, and discussion, all of this has been done successfully and smoothly as all the members give their best and being cooperative.